Okay, so what we're going to start talking about today are sort of two things. Uh, Sort of properties of the derivative that will make them easier to compute for more complex functions than what we were dealing with before, and also the first of our set of shortcuts. Okay. Um, so first off, let's just look at how do we denote what the derivative is. Okay. Remember, we defined it this way. Right? And we said that that limit could perfectly well end up existing or not existing, right? Just kind of depended on the function. And that this defined the derivative at a point x. And it was also possible for a derivative to exist at a point x, but not at some other point, right? So could work out at some places, but not others. Um, so how do we notate the answer for this process? Well, one is already here. It's f prime of x, right? But there's a lot of other equivalent notations for the exact same thing. And so let's just write all of them down. Um, okay, all of these mean exactly the same thing. So why do we have like 6 or 7 different ways to notate the exact same thing? Other than to keep you guys like on your toes. Where's our boy? Ah, the old not feeling well excuse, huh? Is this like in E.T. when he gets out of going to school by faking a fever? Okay, well, that works too. Um, okay, so yeah, so why do we have basically 6 or 7 different versions of the same thing? Well, part of it is who came up with the notation. So these two are due to Leibniz, and these two are due to Newton, and they both sort of independently discovered slash invented calculus at roughly the same time, but they use different notations. And historically, um, you might say, well, shouldn't one of the notations have won out, namely who came up with it first? And oh, believe me, was that the subject of quite the controversy in the 17th and 18th century, was who really invented calculus. Because if you were British, or who did you believe invented calculus? Well, Newton, of course. And if you were not British, then it was, yeah, the other guy, right? Even if you were French, because at least, he might have been not French, but at least he wasn't English, right? Um, so, yeah. And then these other two notations, particularly this one here, um, you'll maybe see in further math classes. So if anybody, like some of you guys are interested in doing like engineering or something, or economics, you might see that notation in later classes. So anyway, so they all mean exactly the same thing. Okay. Now that said, which ones do I tend to use, particularly in a Calc 1 class? I'm going to be probably using one of those three. Um, and I switch between them based on the context of what I'm trying to do. And it'll kind of make sense, I think, which one do we use um, when we go there. Okay, so last time, or really the time before, we found two particular results. We found this, and we found this, right? So we worked those both out with the limit definition, I think 2 classes ago, and it was a little messy and whatnot, but this is what we ended up getting in the end, okay? Okay, so let's do a couple of other ones by using our head here. Okay, do we have to do the limit definition for this question? I mean, we certainly could. Okay, why don't we have to do the limit definition here? Okay, yeah, Jaden. Yeah, what does a derivative mean? It means the slope of a tangent line. Well, what is the slope of a horizontal line, no matter where you are? So what should this be? I'll take 0, right? Okay, now, if we had gone through the limit definition stuff, guess what we would have computed? Exactly that, okay? But knowing what the derivative is supposed to mean means we can get away without doing it. Okay, similarly, what about if we have just x? Okay, we get 1, and where did 1 come from here? It was the slope of the line, right? So what's the line y equals x? What's its slope? I'm sorry, this way. It's 1, right? Well, okay, what is the slope of a tangent line to a straight line? Well, that line is already tangent to itself. Okay, so what's the slope of the line in this case? 1, and that's true everywhere, right? So its derivative is exactly 1. Okay, so those two functions are really easy. Okay, now let's spice it up just a tad, because what about if I had something like, well, what's the equation of any old line, except for a vertical one, of course? Yeah, mx plus b. So what's the slope of this thing anywhere? M, and so what should the derivative be? That's it, right? Okay, do we buy that one? Okay, so what we've effectively just discovered, in some sense, is wouldn't it be logical to suppose that the derivative of mx plus b is equal to the derivative of mx plus the derivative of b? Okay, wouldn't that be nice? Okay, and that is true. Okay, now what's the derivative of mx? M, okay, and we can even go further to say that it's this. Okay, if we have a constant out front, what is the, like, if I were to graph x versus mx, what does the m do to the graph? So x is a straight line, mx is also a straight line, but what does multiplying by a constant do to the graph? Yeah, it shifts it, or sorry, scales it. And if m is bigger than 1, this corresponds to like stretching it vertically. And if m is less than 1, it corresponds to squashing it vertically. And if it's negative, it'll flip it over the axis also. Okay. Now, in the case of a line, you can think of a stretching it vertically and stretching it horizontally, or squashing it horizontally, as kind of being the same thing. In general, you can't, but um, yeah, okay. So should we expect that this is the case? Yeah, okay. Now, this only works, by the way, because m is constant. If this is not a constant, so like if you had like an x times an x, this wouldn't work. There's a different rule for that, which we'll talk about next week. But for now, this works, okay? What did we say the derivative of a constant is? 0. What's the derivative of x? And what do we get? 1 times, does that jive with what our, you know, uh, thought process said it ought to be? Yeah. Okay. So now that's almost too easy, right? Because it's a straight line. Yeah. Okay. It's a straight line, nothing fancy. Um, yeah. Okay. So does that make sense? Okay, so look down there at the bottom of the page. What we basically have just used are those two basic rules, okay? The sum and difference rule and the constant multiple rule, okay? And which will allow us to take a complex function and break it into lots of independent pieces, deal with the independent pieces, and then just add up all the answers, right? Which seems logical, right? Now, why do those properties hold? Well, remember, how is the derivative defined? It's defined in terms of a limit, yes? Well, isn't the limit of a sum the sum of the limits? We already established that back, a few weeks ago. And so the derivative sort of inherits that property. Okay, does that kind of make sense? Yeah. So so that's basically the proof is that hey, the derivative is a limit, so it kind of inherits the same property. Okay, so the power rule. This is the fun one. Okay, so what did we get when we did x squared? We got 2x, okay? Now, you might look at that and say, oh, that's an interesting pattern, right? The 2 seems to be kind of logical here. All right, so any guesses? Yeah, 3x squared. Okay, now how did you do that? What you were doing was you were noticing this pattern, okay? So you pop the power down, then you take 1 away from the power, and that's it. Okay, now, do I know for certain that this is correct yet? I mean, I do, but do we really know that that's correct yet? So how do we need to prove it? We got to do the limit definition. All right, so buckle your seatbelts. Let's do this. That's what we got to do, right? F of x plus h minus f of x all over h. All right. Now, if this were x plus h squared, we'd know what to do. We need to FOIL it. Well, now what do we need? Yeah, we need the heavy duty, industrial strength FOIL, right? And it turns out to be this. Okay, how was I able to do that so quickly, other than being the professor? Huh? Mm-hmm. But I didn't just memorize it. You could have given me x plus h to the 27th, and I could have still written it down because I know the pattern. And do you guys remember the pattern for these things? What are they given by? What are these coefficients given by? Hmm. Who remembers Pascal's triangle from high school? You do not remember that from high school? That was never talked about in high school? Oh, that is just soul crushing. Probably algebra 2. You're not elephants? You forget things? Oh, okay. All all right. So what this does is it gives you the coefficients of x plus y to the something, okay? Where the top row is that something being 0, then 1, then 2, then 3, and so on, okay? So if you raise x plus y to the 0, what do you get? Well, 1, because anything to the 0 is 1. If you raise x plus y to the first, what do you get? 1x plus 1y, right? If you raise it to the second, what do you get? x squared plus 2xy plus y squared. If you cube it, what do you get? X cubed plus 3x squared y plus 3yx squared, or sorry, 3xy squared plus y cubed. And this pattern continues. Okay, now it gets even better. These numbers, how do I generate them? There's a couple ways to think about it. One is the 3 is the sum of the two numbers above it. 4 is the sum of 1 and 3, 6 is the sum of 3 and 3, and that pattern continues also. Okay, am I blowing some minds here? No? Well, if you've already seen it, then yeah, your mind was blown previously. Okay. Wow, right? It gets better. There's a completely different way to think about where these numbers come from. All right, so let's take this case, okay, where the exponent is 2. All right, so I have two objects. How many different ways are there for me to select 0 objects out of a set of 2 objects? There's exactly one way to do it. I don't do anything. How many different ways are there for me to select 1 object out of a group of 2 objects? 2 combination 1, which is 2. What about if I pick 2 objects out of a group of 2 objects? There's only one way to do it, right? Okay, so let's go down to the next line. How many ways are there for me to pick 1 object out of a group of 3 objects? How many ways are there for me to pick 2 objects out of a group of 3 objects? It's also 3. Okay, now let's think about why. Picking 2 objects out of a group of 3 is the same as picking 1 object to not pick, right? So there's sort of a natural symmetry here, right? There you go. Okay, so these coefficients are called binomial coefficients because we're raising things to powers, but it turns out that they also come up in sort of probability kind of stuff. And in fact, you can write them as, did you guys ever see this in high school, this notation? Or you might have seen it as for something like that. Okay, combinations. Did you ever talk about combinations and permutations? Where did you go to high school, Julius? Huh? Fordage? Portage. Oh, the region. Well, that explains it now. Okay. Um, right. So, any of you guys who are interested in studying probability or financial math or stuff that involves probability, like these things are going to come up left and right later. Okay. So, anyway, there's this nice pattern that I happen to know, right? And what happens if you don't know the pattern? Get to foiling. You got to do a lot of foiling and hope that your bookkeeping is correct. Okay. Or you could, but what happens if you don't have a calculator or aren't permitted to use one? I know, right? Well, and this is what I love, right? All my teachers in elementary and middle school would be like, it's not as if you're going to all walk around with calculators in your pockets in the future. And well, yes, actually, we do. They're called cell phones now. Um, so, yeah. Uh, anyway, point being, right, this pattern is nice because it means we don't actually have to multiply everything out. We could, but we can get away without it. Okay, so if I come back up to here, okay, so did anybody not see Pascal's, raise your hand if you did not see Pascal's triangle in high school. Okay, raise your hand if you did not see this like combinations and permutation stuff in high school. Okay, Patrick, do you remember high school? Some of it? Mm. Were you too busy partying? Uh-huh. Yeah, typical beta. Yeah. Hmm. So, all right. Oh, and I forgot to put the limit out front. Sorry. I know, right? They'll just hire anybody to teach math here. Okay, so if we go through and start canceling stuff, what are we going to get to cancel? The x cubed with the x cubed, and that's it initially. So we'll have 3x squared h plus 3xh squared plus h cubed all over h. Okay? All right, so now what's our usual trick? Yeah, cancel the h, so let's factor one of them out and cancel, and so that would leave us with 3x squared plus 3xh plus h squared. Okay? And then what happens when h goes to 0? Only one of them survives, the 3x squared. So there we go. Okay? We? Okay. All right. So let me let you guys scribble that down uh, and see, pause for any question, preguntas, and or fragens. Gucci? Yes. Yes. Yes, exactly. 1, 6, 15, 20, 26, 1. So it always has ones on the outside. And then the stuff in the middle, you just add up the two numbers that are directly above. Okay. And so also every line has one more number accordingly. Okay. Yeah, and if you want to look this up later, this is called Pascal's triangle. Okay. Um, so if you want to look it up on like Wikipedia or something, Wikipedia, especially when it comes to like sort of fundamental mathematical articles, it's usually pretty good, right? There's a lot of really good writing on things like that. I know it may come as a shock to hear a professor being like, "Yeah, Wikipedia is great." Yeah. I mean, okay. So, what are Wikipedia's articles good for? Let's just have that chat. To find other sources and to just get a brief overview as to what the heck the topic is. Okay. Now, where you have to be a little careful is if you, for example, if you go to the Wikipedia article on Ukraine today, okay, there might be a little bias going on, right? Now, it's probably getting moderated back and forth, right? But so if you pick a topic that's politically charged or otherwise controversial or something like that, then it's, take it with some grains of salt, okay? But like anybody, does really, is there going to be somebody who has an axe to grind over Pascal's triangle? Not really, no. Okay, so it should be fine. Huh? Yeah, okay. There could be somebody trolling you. Okay. And in fact, every now and then something funny happens like that. So, um, and I know like Stephen Colbert has done some joke stuff where he's had people like edit Wikipedia to be funny. Um, so this was maybe 7, 8 years ago. I don't know why I did this, but I looked up the Monon Bell game Wikipedia page. And, it talks about the history of it and where the railroad bell came from and had, sort of the current, stats as to how many wins each team had and how many ties there were and so on. Um, but then it also had like a little table that had information about both schools. And it's like Wabash, location, Crawfordsville, student population, about 800 and something, you know, uh, all male in parentheses, right? And then DePauw, Greencastle, 2,000 whatever students, parentheses, all female. And I'm pretty sure I took a screenshot of it. Now, of course, I can't find where I put that screenshot. Now, of course, that got edited like the next day. But for that one 12-hour period, it was the most hilarious thing ever. Huh? Yeah, exactly. Um, so, anyway, right? Okay, so now that we know this derivative, let's actually use it to do a couple of things. So, why don't you guys work out 2a and think about how you might do 2b, okay? So we already know the derivative. What we want now is an equation of a tangent line at a particular point. Okay, so do we have all the pieces that we need to do it? We know the derivative, and we know a point because it's given there as x equals -1. Okay, so take a second to work that out, and let's see what you guys get. Oh, yeah, I did. I'm sorry. I'll pass them out. Okay, so while you're doing that, I'm going to go grab another water because I'm about to die of thirst. So what do we need? Point and a slope. All right, so what's our point? -1's the x-coordinate. What's the y-coordinate? Ah, careful. It's not 3. -1. How did you get that? To the original function. You guys plugged it into the derivative, which we do need. The slope is 3. Okay? So, you fool, you fell for one of the classic blunders. No, Princess Bride. Have you guys all seen that movie? Who has not seen The Princess Bride? You have homework this weekend. Okay. Yeah, because it's a hilarious movie. Okay. So, yeah, so this actually illustrates a point, pun intended here. Yeah. Where do you get the y coordinate from? The original function. Where do you get the slope from? The derivative. Don't mix them up. Okay, because if you use the derivative, you're going to get like you can't mix the slope and the point, right? They're not likely to be the same number. Okay, so now that we have those two things, what's our equation? Mm-hmm. Y plus 1 equals 3 times x plus 1. Okay, good. Now, if I wanted to graph this, like with Desmos or something, what do I need to do next? Yeah, I'd need to, at minimum, I'll just go ahead and put it in mx plus b form. Okay, is that all right? Okay, so what I want you to do is approximate this. Okay, what is the exact answer? Is whatever this is, right? All right, and let me just cheat, and we actually should have guessed that was coming. Haha. You see, the key to good comedy is making sure to reference back to a joke later in the thing. Yeah, okay. Oh, yeah, sorry. Okay, but how would I have computed that by hand? Well, okay, yes, in this case, right? But like if I sat down to multiply it, right, that'd be a fair bit of work, yes. Yeah, okay. So like maybe you learned some kind of trickery in school for how you could do kind of fast multiplication. And of course, the numbers are relatively small here, so it's not going to be that bad to do it by hand. But what about if this was like a 1.1 was like had 10 decimal digits? Do you want to really sit down and multiply all that crap out? Probably not. Okay, not by hand anyway. So what could we do instead? What we could do instead is let me call this function that we came up with L of X. L because it's a line. Okay. What I want you to do is plug in that. What do you get? Put that away. You don't need it for this. Yeah. So I'd get what? I'd get 3 times negative 1.1 plus 2. Close enough. Okay. So this technique of using the tangent line as a way to approximate the original function, is it ever going to be perfect? There's only one place it's perfect at x equals negative 1, the point of tangency. The further away you get from that, the worse it's going to get. But if you're really close to it, yeah, that's, pretty close. Okay, does that make sense? Okay, so, and we'll come back to this idea of using the derivative to approximate a lot. Okay, um, okay, so, and let's sort of see why it works. Let's graph both of these things. All right, so what was our original function, x cubed? Where's the exponentiator here? Huh? Oh, there it is. The derp. Okay, so we got x cubed, and then what was our derivative equation? The L of x, 3x plus 2, right? Okay. All right, and then let me zoom out and get over here. Okay, so first off, does it look like the line is in fact tangent to the blue curve, the cubic, at the correct point? Yeah, looks good. Okay, and second, the reason why what we did in the previous question makes sense is because what is the difference between the y values of the blue curve and the black line if we're really close to x equals negative 1? Not a lot. It's a really small difference between the two. And the closer you are to negative 1, the closer those things are to each other, to the point where you almost can't even tell the difference between the two graphs if you're really close to negative 1. Okay? So this is sort of what justifies that this tangent approximation that we just did a second ago is actually worthwhile to do. Okay? Now, is it going to be a good thing to do if we wanted to know what f of 0 is? Hell no, right? because that's so far away that the difference between them is, well, 2 versus 0, right? That's a big, big difference. But if we're really close to the point of tangency, this isn't all that bad, okay? And it turns out that there are ways to make this thing, to improve these estimates, okay, that are called Taylor polynomials, which is something that we'll look at a little later, well, much later in the semester, but also those of you who go on to take Math 112 will do this like a lot, okay? So anybody planning on taking Calc 2 after this? Yes, good. Yes, good. Arthur, yes. Have you signed your deposit check yet? No? Patrick! Yeah, I did. You're not helping. You guys are supposed to be like trying to give him inside tracks into your fraternities and stuff. Hmm. Or is this technically dirty rushing? Oh, okay, that's dirty rushing. Well, definitely don't rush beta. Mhm. Hey, can't be dirty rush if you're not in a fraternity, right? So, okay. All right, so does that make sense? And then there's our graph, right? And we could, of course, have sketched these two things. Um, yeah. All right, so flip it over. And oh, it gets so much more spicy, right? We just went from the honey barbecue to the, what's the other barbecue at B-Dubs? Hot barbecue? No. We went to maybe Buffalo, like mild next, right? So, yeah, we're not even close to the ghost pepper wings, okay? The blazon that has like ghost pepper and Carolina Reaper and yeah. Is anybody a real spice head and like things like nuclear spicy pain? Yeah. Yeah. Well, okay, because when all of that all those pain receptors are firing, then you start to get endorphins. And if enough of them are firing, so when I had ghost pepper wings for the first time at B-Dubs, I actually started hallucinating. Okay, now it wasn't like full on acid trip hallucinating. Okay, it was much more mild than that, but it was definitely a very slightly altered state of consciousness. Yeah, they were so tasty. The flavor was great. No, actually, ghost peppers and like habanero, for example, has a natural sweetness to it, and the ghost pepper had a nice kind of smoky flavor too. Now it was also intense burning, but um, yeah, like charcoal. And how often have you been eating charcoal to have a basis for comparison here? Well, okay, fair enough, right? Um, okay, so let's look at number 3 and 4. Okay, so work those two out real quick, okay? And let's see what you get. Okay, because what's the trick here? You're going to be using the power rule, but also, do you have to do, you can do each of these piece by piece, right? Okay, that fast. You guys agree? Yeah. All right, try number 4. What's 3 times 2? Right? Power comes down front. Did I mess something up? Oh, yeah, yeah, sorry. Any other F ups on my part? No? Huh? about the plus C. Yeah. Uh, all right. So take a second to work that one out. Hand on top of your head when you got it. Yes, sir. It's 14 times 4 because I didn't want to actually multiply out whatever that is. Oh, it is 56. Okay, let me rewrite that then because I was being lazy. All right, hand on top of your head when you've got it. I know it is. The tricks are nice, right? Until Monday, right? When they start getting nasty. Okay. Everybody got their hand on their head almost? Yeah, we good? Okay. So what'd you get? 7x to the sixth, 12x cubed minus 12x plus. How many of you wrote 2 times pi to the first? Nobody fell for the trap? Why not? Because pi is a constant. Okay, so what was the trap answer for this last part? 2 pi to the first. Okay, but why is that different than the other terms? Because the other ones are all in terms of x, and pi is not an x last time I checked. And second, what is pi? It's a number. I'm triggered right now. Okay. Um, although, given that we're in Indiana, I'm surprised nobody is like, yeah, pi is equal to 3. Um, so, um, okay. So actually, let me pause for a moment. Right, that's the kind of crap you'd expect out of like Alabama or Arkansas or whatever, right? Yeah. There was actually a bill at the Indiana State Assembly about a little over 100 years ago that would, amongst other things, make pi equals 3 the official value of pi in the state. And I'm only partly exaggerating here. So, okay, what it really was so in mathematics, there are lots of people who are very good at mathematics and get degrees in it and actually practice it, you know. Um, but okay, so let me actually make an analogy, right? Medicine. There are lots of doctors out there, and nurses, and nurse practitioners, and physical therapists, and phlebotomists, and pharmacists, right? All of these different professions that are all connected to healthcare, and they all play different important roles, okay? Mathematics is kind of like that, right? You got your PhD mathematicians, you got computation people, you got, undergraduates, right? It's one big family. Okay, but you would all say, hopefully, that all of that medicine is all legitimate medicine. Okay. And then you've got the people that are trying to sell you like healing crystals, right? Mathematics has healing crystal people too. We call them cranks who have who think that they've discovered results that we've proved can't happen hundreds of years ago. Okay, but they've discovered the truth, and then sometimes and that the big math is out to get them and to suppress their discoveries, right? So there's also some conspiracy theory elements to this. No, that this 100% exists. Big, well, yeah, big math. Okay, yeah. So anyway, cranks claim to have discovered stuff, and there was this guy who claimed to have discovered all these amazing things. And one of the consequences of his discoveries, if you accept it, would be that pi would equal 3. And what the bill was is he basically wanted the Indiana legislature to recognize him as the discoverer of all these amazing things. And in exchange, he would allow his amazing discoveries to be taught without royalties for free in Indiana public schools. We should have taken it, right. Fortunately, an actual mathematician from IU happened to be at the state capitol and somebody handed him the bill, and he looked at it and it's like, it's not worth the paper it's printed on. Okay. And fortunately, it went nowhere. But yeah, like I said, this is the crap that you'd expect out of Arkansas or Alabama. And no, it happened right here in Indiana. Okay. Huh? Yeah, well. Okay. So, one last thing before we quit. The power rule actually works even if the power isn't a positive number. Okay. So, for example, we previously had dealt with this case, right? How can I think of that as something to an exponent? Uh-huh. And what's the derivative? 1/2 x to the minus 1/2. The same rule. Exponent comes down, take 1 away from the exponent. Does this jive with what we had when we did this the long way? It does. Okay. So the power rule will work. What was the other one that we did? 1 over x. How would I write that with an exponent? X to the minus 1. What's the derivative? Negative x to the minus 2. Is that what we got before? Yep. Great. Okay. So the power rule works even if the exponent is not a whole number. Okay. Now, one warning, the exponent must be a number. Okay. So could I do this for like e to the x? This does not work for e to the x because the exponent is the variable and the base is the number. We need a different rule for that case. Okay, so does that kind of make sense? All right, so just quick reminder, what are we doing on Monday? Well, we'll have class, obviously, but what else are we doing? Yeah, your next assessment. And I posted the next task a few days ago. A few of you guys have already kind of taken a crack at it. The monk and the monastery. You got to use a theorem. All right. See you later.